In previous videos, we have seen that the power pole is the main building block of voltage source converters. But a single power pole by itself, along with some passive components, can form a full-fledged power converter. So this video focuses on the analysis of single power pole based power converters. We have seen earlier that the power pole is just a bipositional switch formed by two on-off switches which switch complementarily at high switching frequencies, meaning when the top switch is on, bottom switch is off, and vice versa. The signal Q sub A that is the gate drive for the top switch. So if Q is 1, the top switch is on. If Q is 0, the top switch is off and the bottom switch is on. QA itself is in turn derived from this control voltage VCA, which is the output of some closed loop controller, and Q is derived by this pulse width modulation process. So when VCA is higher than a sawtooth or a triangular waveform, Q becomes 1, and if not, Q is 0. The power pole, in addition to having these bipositional switch controlled by this Q sub A, also need to meet two constraints. One is the voltage across the power pole, across the two end positions, has to be a non-pulsating smooth DC voltage, and the current from the midpoint, the pole, has to be again a non-pulsating or a non-switching current. Okay, then through a simple analysis looking at these waveforms, we determined that the average of the pole output voltage VA with respect to the DC negative, the average value is 1/2 of the DC voltage plus 1/2 of DC times the control voltage. So we can think of the single power pole as an amplifier with a gain of this 1/2 of DC voltage. It amplifies the control signal by that gain, plus a DC offset of again 1/2 of the DC voltage. Okay, then we also derived the average model of the power pole. It turned out to be an ideal transformer with the voltage port and the current ports forming the primary and secondary respectively, and the turns ratio being the instantaneous duty ratio of the pole. So we have seen that the power pole is the building block, and we saw several examples in previous videos showing converters with multiple power poles forming this power converter for different applications. So as I mentioned at the beginning, a single power pole by itself can be a full-fledged converter along with some passive components, and the simplest example is the step-down or the buck DC to DC converter as used in most computer power supplies. We can also have a boost converter using just a single power pole, and this has for example wide applications in photovoltaic interface, where they can convert the low voltage from the PV arrays to a higher voltage suitable for grid interface. Or this could be used as a bidirectional converter that interfaces for example two batteries, or it can also be used in solar inverters that have battery energy storage, and this converter can be the interface between the DC link of the PV inverter and the battery. A single power pole can also be a full-fledged DC motor drive, where it can be used to control the speed of the DC machine as well as achieve regenerative braking. And finally, a single power pole, again in the PV application, can also be used as an active filter. So when we study PV inverters in detail, we'll see the real application of active filter in supporting the what is known as a double line frequency power pulsation. A single pole is really a two-quadrant converter because its output voltage VAN can only be positive. If you look at the instantaneous VAN, it can only be either VD, VN, the DC voltage, or 0, never negative, and its average given by this expression D times VD can also only be positive. It can vary from 0 all the way up to Vn and can be controlled continuously. but the current can be bidirectional. So we are talking about the pole current or the output current or this inductor current, and the top switch and the diode can support either positive or negative current during Q equals 1 period, and when Q is 0, the bottom switch or the bottom diode together can support again current either positive or in the negative direction. So therefore the instantaneous current can be positive or negative, therefore and thereby the average current can also be either positive or negative. So that information is given in this figure. So the voltage is only unidirectional and the current can be both positive and negative. So this is the capability of the single pole, and the limits are given by the VAN average limit is VD, and the current limit is really the ratings of the switches. So the current can be anywhere between minus Imax to positive Imax, where Imax is the maximum current rating of the switches. So with the unipolar voltage and bidirectional current, the single pole converters end up achieving the capability for bidirectional power flow. So this allows the single pole converters, for example in DC motors, to achieve regenerative braking or be able to charge and discharge a battery using the same converter in battery management applications. So now we know that the average model of power pole is just an ideal transformer with turns ratio equal to the duty ratio. So to get the average model of the complete single pole based power converter, all we need to do is to replace the switching power pole by its average model while retaining all the other components like the input source, the L filters, and the other components. So this is the complete average model of the single pole power converter, and the D is instantaneously varying. It is the instantaneous duty ratio, and just from the transformer principles we can see that the average VAN bar is D times VD, and the D itself is 1/2 plus 1/2 of the control voltage as we derived in an earlier video. The average model that we derived is valid in transients. So if you want to do your transient analysis, then for example applying KVL around the loop on the secondary side, the inductor voltage is VAN average minus the resistive drop and this voltage source E sub A as given by this equation. So that's the voltage. So L di over dt, where I is this pole current, same as the inductor current. So that is equal to the inductor voltage, which is as we saw given by this expression, where VAN average itself is D times VD, and the current drawn from the input source can be written by the transformer principle as simply the turns ratio D times the secondary current IA. So that gives the average current drawn from the DC source, again in a transient sense. But if you're interested in doing a DC steady state analysis, then we can further simplify this model. So we know that in steady state the inductor current is not changing, or di over dt is 0, or in other words we can in DC steady state we can short circuit the inductor. Its voltage is 0, therefore it's shorted, and then the inductor current can be given by this algebraic equation, which is simply VAN minus this EA divided by the resistance RA. So we saw that because of the bidirectional current capability, the power flow can be in either direction, and depending on the power flow direction, we can actually have two modes of operation for this single pole converter. So the buck mode and the boost mode. And what determines which operating mode we are in is the whether VAN average is more than or less than the E sub A. So if VAN average is higher than E sub A, then we are in the buck mode of operation. the power flow is from the high voltage side to the low voltage side. So that is because when VAN is higher, the current flow is actually from VAN towards E sub A, left to right on the secondary side, and therefore current is actually drawn from the input source, resulting in power coming from VD and delivered to E sub A. Whereas in the boost mode, VAN average is kept lower than E sub A. Therefore, the current direction is actually in the reverse direction. I sub A is actually negative. And this corresponds to the boost mode, where the power flow is actually from the low voltage side to the high voltage side through the bipositional switch. So the buck mode, for example, could correspond to the normal motoring operation of a DC motor, whereas the boost mode can correspond to the regenerative braking in the DC motor. Or the buck mode corresponds to power flow from a high voltage battery to a low voltage battery, and the boost mode is just the opposite. Also notice that there is actually no change in the circuit configuration to go from the buck mode to the boost mode. All we need to do is to change the D by controller, such that the VAN average is the desired value that determines whether it is boost mode or the buck mode. Okay, so that was the average analysis. Now let's get into some switching frequency level analysis of the single pole power converter. We'll begin with the operation in the buck mode, and the next slide will be the boost mode. So here is the PWM process, your triangular waveform compared with the control voltage VCA, and up to this point where VCA is higher than V triangle, Q is 1, therefore VAN is instantaneously, because the top switch is conducting, VAN is same as V sub D as shown here. And from this point up to this point, clearly the VCA is less than V triangle, so Q is 0, the top switch is off, bottom switch is on, therefore VAN instantaneously in that sub-interval is 0, and the process repeats. So this is buck mode, which means we need the VAN average, which is denoted by this dotted line, to be higher than E sub A. We need to control the D, the VCA, such that VAN average is higher than E sub A. Okay, next we look at the inductor current waveform, which is shown here. The average value of the inductor current, that can be easily determined. Actually, we did this in the previous slide. So this is IA is VAN average minus EA over RE. So that is because in DC steady state, inductor is like a short circuit. Therefore, just KVL around the loop without the inductor gives this equation. So that's just the average value. But what we are interested in is the complete inductor current waveform, including the switching frequency component as shown here. So by looking at the inductor current waveform, we can clearly see that it is actually a piecewise linear waveform. And that is because the voltage across the inductor is actually a switching waveform with a constant magnitude during this on interval T on, a positive value, and a negative value during the rest of the period during this off interval. So the constant magnitudes across the inductor, the voltage across the inductor during both the on and the off interval, is because of this small ripple approximation, which says that the high frequency content in the voltage drop across the resistance is negligible, and this E sub A is actually a DC voltage source, so its high frequency content is also 0. So with that, we can actually write the slope of the inductor currents, or actually the slope is the VL over L, inductor voltage divided by L, and VL during the on interval is this expression. It is VAN, which is VD during that on interval, minus the resistive drop and this E sub A, both of which are assumed as constant DCs. Okay. And then the slope of the inductor current during this off interval is again VAN minus, so VAN is 0 because the bottom switch is on, minus the same two quantities, IA, RA, and minus EA. That divided by the L gives the slope during the off interval, and that is a negative slope, so the current is actually falling linearly. So once we know the inductor current, we can actually draw the current through the top switch, the current through the bottom switch, as well as the current taken from the input. In fact, the input current is exactly same as the top switch current. Okay, so that is shown here. So this D is the DC, the A is for the pole A. So the DC current due to pole A is this IDA. So this is exactly same as the inductor current that we drew earlier, but only during the switch on interval, only during the Q equals 1 period, or only when the top switch is conducting. Okay? So during this Q equals 0 period, there is no current from the input. The inductor current is actually supported by the bottom devices, either the MOSFET or the diode. So this is the instantaneous waveform for the input current, and we can actually get its average, and that should be equal to D times the IA. Okay? Instantaneously, it is given by this expression, where it is the product of QA, which is the switching signal, times this I sub A, okay, which is this expression. We can also go ahead and draw the waveform for the bottom switch current, which is not shown here, but that will be same as the inductor current only during the off interval when Q is 0. So here the current would be 0. The current will jump to this waveform during the off interval, back to 0 for this entire on interval, and so on. The concept is very similar for the boost mode of operation, even though the waveforms look quite different. Because it is boost mode of operation, this VAN average, which is the average of this waveform, is actually less than E sub A, and the current therefore is negative, and but the input current is given by the same expression, D times IA, and that is also is negative, less than 0. Okay. So these are the switching level waveforms of the inductor current, and then the input DC current, both are negative, but you can see that the it is still a piecewise linear waveform for the inductor current, and the current is actually increasing during the T on interval here and here, and during the T off interval when Q is 0, the current is actually falling. Okay? It's very similar to the buck mode of operation. These slopes are also given by the same exact expression that we had for the buck mode of operation. So this is the DC input DC current, and once again it is same as the inductor current during the T on interval, and it is exactly equal to 0 during the Q equals 0 period, and its average value given by this dotted line again is D times IA average, and it is obviously less than 0. We will stop at this point and continue the further discussions related to high frequency modeling, high frequency ripple analysis in part 2 of this video.